we will now look at synchronizing with atomic variables and memory fences. And it's of course sufficient to use only atomic variables and no fences, but if the memory order for the accesses to the atomic variables are relaxed, then we need to use fences to do the release and acquire operations. One important thing is that we need to know which instruction is performed before the other. And this is not always specified in C or C++. Well, of course there are rules, but it's easy to make terrible mistakes. Well, it's not easy, but it is possible. Okay, so there is something called sequenced before, and that is when some instruction is guaranteed to be performed before the other. Okay, and that is most simply explained using sequence point. A sequence point is, for instance, a semicolon, a function call, comma operator, or the evaluation of the left operand of these three operators. And if we don't have a sequence point, then the evaluation may be reordered in non-intuitive ways. And why is it so? Well, it is to make the language as fast as possible, languages as fast as possible, in order to let the compiler decide which is most efficient. And it's just terrible lousy C code if we if the output of the program depends on the compiler's decision of which instruction should be executed first. Okay, so let's look at a terrible example then. So here we initialize two variables and declare a third. And here, well, this label, it's just a reference in the slide, but it has no other purpose. Okay, so can we know the value of W? Unfortunately not. Well, not unfortunate, but we cannot. And the reason is that which operand of a binary operator, not these binary operators, but add, for instance, which one of these operands is evaluated first is decided by the compiler. It's so-called unspecified behavior, meaning the compiler does not have to document it, which one it will do. It's just what it thinks is best to reduce the energy waste of running the program. Okay, so it may do this first, or it may do this first, and depending on which it decides to do, the value of W will be either 12 or 20. Okay, so that was unfortunate if somebody didn't know that. And if we instead would use a comma operator here, then we would force the left operand of the comma operator to be executed before the right operand, the right-hand operand. Okay, so then the value be 16. So sequence points, they are part of determining whether something has happened or not. Okay, so memory fences, they are in Linux terminology called memory barriers. And we have seen the idea before, namely it is the release and acquire, and they have no memory operation, a memory operand. Instead, they are commands to the CPU to wait until something has happened. And for a release, it is a command to the CPU to wait until all the previous writes made by that CPU have completed. And what completed means, we have already seen in previous lectures. Okay. And acquire, it tells the CPU to wait until all previously arrived invalidation messages, which the cache replied to immediately without performing them, until they have been performed. Okay, so there can be several levels of cache memories, and it's the most external level that is that receives the invalidation message, and then it should reply immediately and tell the levels which are closer to the CPU, finally the first level cache, that it should remove them. But it's better to reply at once, so that the writing CPU can get an acknowledgement quicker. Okay, so how do synchronization with fences and atomic variables work? Suppose we have two threads, T1 and T2, and if T1 writes to an atomic variable after the release, and T2 reads it before the acquire, then the writes before the release made by T1 will be visible to T2. So the atomic variable is a variable that you can think of as it says that something has been updated. We'll now look at an example and two ways to write buggy code. So what we have is an atomic object or atomic variable and two threads. Thread 1, I use indentation here to see to show which thread is doing what. And both threads see these global variables. Okay, okay, the syntax is not ideal, but it doesn't matter. You understand what I mean, I'm sure. So thread 1 starts with setting this non-atomic variable to some value, and then it does a release using the fence. What happens then? Well, the CPU for thread 1, it must wait until all others have acknowledged their the invalidation. Okay, and after that, thread 1 can write to this atomic variable, and it doesn't matter which memory order it uses. This can be relaxed. Okay, and then the other thread, well, it waits until it has read the value. And how can it know that it has read the value? It really doesn't matter which value it is, it just that it reads a value written by the first thread. And in fact, either, and it's not only the first thread, it could be additional threads between here. And if they have read, modify, write, and this thread reads the value that was modified, I mean in between with all these threads, but it's sufficient to understand it firstly with only T1 and T2. So let's see. But what I want to say is that there could be multiple threads in between here, but just ignore them for the moment. Okay, so the first thread reads something, and then the second thread the first thread writes something, and then the second thread reads something. But how can it know that it has actually read something that this thread wrote? Well, if this thread wrote a 0, then how could it know that it has already done it? It can't. So it has to read some new value, and therefore when it can leave this loop, it knows that it has read a variable that the other thread has written. Well, if the program was written in that way. Okay, and then when it has read this atomic variable that the other thread wrote, it can do an acquire. What happens then is that it has got all the previous invalidations, and that means including U. So now it can read U. And if we would just run these two threads, starting them, then there is no order between them at all. What is required is that when the second thread knows that it has read a value written by this thread, or being overwritten by other threads which have read and written the same variable, then it's also sufficient. Okay, so what happens then is that the modification of U happens before the read of U by the other thread. So how can we look at this in a somehow abstracted way? Well, the operation is that we synchronize with, just as we did synchronize with mutex, we can use synchronize with fences. Okay, and what we have is this A, X, Y, and B. And A and B, they are the release and acquire fences, and X and Y are the writes and reads on the same atomic variable. Okay, so if we have them, and in this order, first write some arbitrary data that is non-atomic, and then do a release. Okay, so we send out the invalidations, and then we modify this atomic variable. Okay, and this the other thread reads this. Okay, they can be in relaxed memory order, and here we can see Y reads a value written by X. This instruction here reads the value written by X, or the hypothetical release sequence headed by X if it were a release. What this means is that there could be other threads doing read and write with release on M. Okay, and we should also note that the A or B can be replaced with an atomic operation. If X was a release operation, or Y was an acquire operation, a load with acquire, or X a store with release, then they can be skipped. So it's not necessary that both use fence. One or both could use atomic store I mean, with both could skip the fence and just use atomic operations with the proper release for X, or acquire for Y. So how can